What's up everybody, welcome to another video. Hope you're ready to flex those brain muscles. In this video I'm going to introduce the idea of finding limits algebraically. It's a very common thing we're asked to do in calculus. We're given a limit like this without a graph or access to a graphing calculator, and we're asked to find the limit. So in this video I'm going to introduce how we begin to think about problems like this. First, what we always want to do is start with direct substitution. What that means is we always want to start trying to evaluate these limits by plugging in the number that x is approaching, right? We want to plug -1 in this case in to the actual function and see what we get. So let's go ahead and try it. In the numerator, I start with -1 squared, that's +1, plus -1, so I can write that as -1, and then we have a -6 just chilling there. In the denominator, -1 squared is again +1 minus 6 times -1. Minus minus, that becomes plus, and 6 times 1 is 6, plus 8, that's just chilling. All right, let's see what we got here. 1 minus 1 is 0. 0 minus 6, -6. So we have in the numerator. And in the denominator, we have, let's see, 1 plus 6 is 7. 7 plus 8, 15. Amazing. Oh, there's a common factor here. This could actually be simplified. Let's see, 3. 3 is the common factor. -6 divided by 3 is -2. And 15 divided by 3 is 5. So from plugging -1 into this function, we get -2/5. And what that means, when we're dealing with rational functions like this and we're finding limits, if we plug the number that x is approaching in and we get a real number out, which is what -2/5 is, then that's just the limit. And this is one of the reasons why direct substitution is awesome, is because sometimes it just gives us the limit. So I want to talk about why this works. And the reason why this works is because rational functions are what we call continuous over their domain. What that means is, if I'm plugging a number in for x, so let's look at the example I just did. I plugged -1. We can see where that is in the graph. When x is -1, y is -2/5. That's this point right here. If I plug a number into this function and get out a real number, right, that's what it means for something to be in the domain, is that I can plug it in and get out a real number. Then the y value, right, the real number that I get out, the y value on the graph, is the same thing I would get if I approached from the left or from the right, right? That's the same as the limit, and that's in fact what it means to be continuous, right? And this would be the case if I plugged in 1, for example. If I were trying to find the limit of this function as x approached 1, and I plugged 1 into the function, I would get out some y value around here, and we can see from the graph that's the same y value I would get if I traced from the left and from the right. Same thing happens at any number where the function is defined. 3, right? 6 over here, if I plugged in 6, I'd get that y value, and that's also the limit as x approaches 6. So this works for any x value where the function is defined, which is its entire domain. And it turns out this is the case for almost all of the functions we deal with, especially if we're in high school math or even like introductory college courses. You know, linear functions, quadratics, polynomials, radical functions, exponential functions, trig functions, log functions, all these different functions are continuous on their domain. So that means that we can use direct substitution, and if the result is a real number, then boom, that's just the limit. So that's what we're going to practice on this slide. Pause the video, try to evaluate some of these expressions. All right, hopefully you paused and you got it all figured out by now and you're just checking your work. I'm going to move pretty quickly because I'm assuming you're in calculus if you're watching this, and evaluating expressions is probably pretty easy for you. So let's plug in -3. -3 squared is 9. 9 minus 4 is 5. That is a real number, and boom, we just found the limit. All right, let's plug in 1 here. 1 cubed is 1, plus 2 times 1 squared, that's 2, minus 1 plus 5. 1 and -1, those will cancel, so 2 plus 5 is 7. That's a real number, boom, that's the limit. All right, let's look at this radical function. 7 minus 3 is 4, square root of 4 is 2, light work. Let's look at this exponential function, 2 cubed, 2 times, let's see, 4, 8. 8 minus 1 is 7, boom. All right, ooh, some trig, the sine of pi, throwback. What is the sine of pi? Pi is over here, 180 degrees. What is the y value at that point? And it is 0, and that's in fact a real number, and that's the limit of sine as x approaches pi. All right, finally, this is a cool like log rational hybrid that I thought I'd throw in just for fun. When we plug in e for x, what do we get? In the numerator, we get the natural log of e, and in the denominator, we get e. And this is, in fact, a real number. That's the limit. Bonus points if you notice that the numerator could be simplified to 1. The natural log of e is 1. How can we justify that? Well, the base of natural log is e. So this little expression here is like saying e to what power equals e, which is 1. Amazing. Awesome. So again, direct substitution is great because a lot of times it just gives us the limit. But there are some cases where it doesn't work, and this is the primary type of example we see in calculus where direct substitution isn't good, at least not for the purpose that we've been doing it so far. Here's what I mean by that. Let's try it. Let's plug in 1. How do we figure out what f of 1 is? What is the value of this function at 1? Well, this is a piecewise function, and we can call it that. One way to think of it is it's sort of defined in pieces, right? The y value is x minus 2 for x values less than or equal to 1, and the y value is x squared when x is greater than 1. So if we are plugging 1 in, we want to look at this part here, less than or equal to 1. X minus 2 is going to give us the y value. So what is 1 minus 2? That is negative 1. That's the result of our direct substitution. And so it may be tempting to say, hey, direct substitution, I got a number, that's the limit. But here's the problem with piecewise functions, is that they can have jumps like this, which is exactly what this function has. So this function is not continuous on its domain, right? 1 is part of the domain. The function is defined at 1. We just plugged it in and got negative 1. We can see that from the graph, but the function is not continuous at 1. It has this jump. The limit at 1 does not exist. And so what we have to do with piecewise functions is we just have to check left and right limits. I'm going to make an entire video on this. It'll probably pop up on the screen right now. Once it's made, you can check that out. But piecewise functions are an example where our trick for direct substitution, get a number, boom, that's the limit, doesn't quite work. All right, let's dive a little bit deeper into what direct substitution tells us when the function is not defined at the x value. So here's 2 examples. We're going to find the limit as x approaches 2. We can see from the graph there's a hole when x is 2. And then we're going to find the limit as x approaches 2. We can see on the graph there's an asymptote there. All right. So what happens when we plug 2 into this function? In the numerator, we get 2 squared. That's 4. Plus 2 minus 6. In the denominator, we get 2 squared. That's 4 minus, let's see, 6 times 2. That's 12 plus 8. And what does this equal? In the numerator, we have 6 minus 6. That's 0. In the denominator, we have, let's see, 4 plus 8, 12 minus 12. That's also 0. This function is undefined at 2, which made sense. We already knew that from the graph. But in particular, we get 0 over 0. What happens when we plug 4 in? Let's try this. 4 squared is 16 plus 4 minus 6. And in the denominator, we get 4 squared again, which is 16 minus 6 times 4. That's 24 plus 8. So what does our numerator come out to be? Let's see, 16 plus 4, that's 20, minus 6 is 14. And the denominator, we get 16, let's see, plus 8 minus, oh, we get 0. Okay, so it turns out there's a pattern we can notice, and I know we're only looking at one example here, but we can generalize this at least a little bit. And what we could say is that when I do direct substitution and I get a non-zero number over 0, like I did in this case, this always corresponds to a vertical asymptote and means that the limit does not exist. That's what we can conclude from this. Non-zero number over 0, boom, we can just conclude that the limit does not exist. 0 over 0, there is very often a hole. That's what this means. Often a hole, or maybe it's better to say there could be a hole. There isn't always, and that's why sometimes this is called indeterminate form. If you've seen that before, indeterminate, sorry, that's terribly written. Indeterminate form, if you've heard that word before, that's what this means. And that just means that we have to do a little bit more investigating to figure out if this limit exists or what the limit is. But it very often corresponds to a hole with these rational functions especially. And let's dive a little bit deeper into why this is the case. So again, looking at the same function, we can see the function in factored form. We can compare it to the graph. And if you remember the stuff you learned in like Algebra 2, college algebra, whatever it is about rational functions, it's that holes come from these repeated factors that are in the numerator and denominator that can sort of be canceled, right? And when we cancel them, there's no more of these factors left in the denominator. And the reason why this creates a hole is because think about what the value of x minus 2 divided by x minus 2 is for different values of x. The value of this is 1 for every single value of x except for 2, where it's undefined, right? So if I canceled this out, the only difference between this original function and this function I would get from canceling these out is that the original function is undefined at 2, and this new function is defined at 2, right? That's the only difference here. This creates a hole, whereas when we have this situation where we have a factor in the denominator that doesn't cancel out, that's what gives us vertical asymptotes. So I'm going to write that here. Vertical asymptotes come from these types of factors in the denominator that aren't cancelable, whereas these, when they are cancelable, give us holes. Finally, it's worth mentioning, just to review rational functions, this is what gives us zeros. Doesn't help us a whole lot when we're finding limits, but it's worth mentioning. So again, this is very often why it's the case where we plug in 0, we can see there's a hole in the graph, and that's because it's very often the case that it's a cancelable factor, and that when we actually factor and cancel, this is one of our methods for finding limits, is factor, especially with these rational functions, factor and cancel, that when we plug 2 into this simplified version, just that x plus 3 over x minus 4, look what we get. 5 over, let's see, 2 minus 4, that's negative 2. Boom, which we can see is the y value of the hole. Awesome. All right, here's what we can jump into. One example where, again, we do direct substitution. 1 minus 1 is 0. In the denominator, 1 squared minus 2 times 1 plus 1. That's also 0. So we get 0 over 0. And again, this is why we call it, let's see if I can write the word better this time, indeterminate form. Still not that great. I'm sorry. Indeterminate form, because look at this example here. We plugged in 1. We got 0 over 0, right? Maybe looking at the last example, we think, oh, this means there must be a hole. But look what the graph looks like. At 1, there's not a hole. There's actually an asymptote. And here's an explanation for this, which is that we have these two factors, x minus 1 and x minus 1, repeated in the numerator and denominator. But when we cancel them, we are still left with an x minus 1 factor in the denominator, which creates a vertical asymptote, right? In other words, I can't remove the discontinuity by canceling or simplifying. It's just still there. It's stuck. And in fact, these are the exact same function. This x minus 1 with the two x minus 1 factors in the denominator is the exact same thing as just 1 over this, right? So sometimes there's tricky, weird examples like this where we get 0 over 0. The good thing is that even if we think, oh, there for sure has to be a hole, and we continue with our factor and cancel method, eventually, hopefully, we factor and we cancel and we resubstitute, and notice that this time we get 1 over 0, and that means there is an asymptote, right? So not a super big deal, I guess, if you forget this concept, but it's worth talking about because it's cool. Awesome. All right, let's summarize what we learned. Direct substitution, we always start with this. This gives us information. Sometimes it literally gives us the limit, right? Because if we plug in the number and get a real number, that's the limit, unless it's a piecewise function. Those are the weird ones that can have jumps where we need to check left and right limits. In other cases, it tells us 0 over 0, indeterminate, could be a hole. We have to continue with other methods to for sure figure out whether it's a hole and what the limit is. In this case, it again just tells us what the limit is, which is DNE, right? Non-zero number over 0. Asymptote, limit does not exist. We could investigate further if we really want to figure out whether it's infinity or negative infinity, or can be expressed as that, right? If this is the asymptote, and on the left it looks like this, and on the right it looks like this, maybe our instructor really wants us to write that as infinity instead of DNE. And if they do, then we need to investigate further, but tells us there's an asymptote. I'm fine with my students just writing DNE because that is true. Awesome. What happens with indeterminate? We have 3 main methods: factor and cancel, which I kind of touched on in this video a little bit. Rationalization or conjugate method. We often do this with radical functions where you can multiply the numerator and denominator by something and remove the discontinuity, find the y value of the whole. And finally, trig identities that we can apply. We can cancel things and again remove the discontinuity, so we can substitute and find the limit. This is a summary of the different techniques we have and approaches to finding limits algebraically. Hopefully this video helps. That's it for now. Like and subscribe. Most importantly, keep flexing those brain muscles, and I'll see y'all later.